Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 4.2 on area and summation. So let's get right to it. Today we're going to be talking about sigma notation, something that we've talked about before in pre-calculus and maybe a little bit earlier on in the year. And we're going to write and evaluate a sum. We are going to talk about the concept of area in the context of area under a curve, and we're going to approximate the area of a plane region, and then we're going to do that using limits. So, just a little bit of review, the use of the integral, which is what we're working forward to. And so when we say the most basic function of the derivative is to find the slope of a tangent line at a point, that's what the derivative does. All right. And so similarly, the integral has a basic use, and its basic use is to find the area under a curve over a closed interval. And what you can think of is we're going to find a bunch of regular shapes and let those things shrink so small that they actually become the area under an irregular curve. Now, when I say the area of an irregular region can be found by finding the sum of the regular parts. So let's say I draw something like this, just as a for fun kind of thing. All right. We don't have necessarily an equation that calculates the area of that particular thing. If I make all the dots line up nicely, you know what? Let's make this one just a little bit longer so I can illustrate that. So here's what we can do. Because I see some right angles, what I could possibly do is change some of this, and let's say I find the area here. Well, this area is a rectangle. I could divide it up there. There's an area of a triangle. Here's another rectangle and another triangle. I could find all of those areas individually. And if I find the area of this polygon A, this polygon B, this polygon C, and this polygon D, and add them all up, well, now I found the area of the total region. So we do something like that when we're talking about continuous functions. So the sum of the area of the rectangles is an approximation of the area under the curve. So let's say, just as a for instance, I have this curve right here. And again, I don't know anything a whole lot about it, but I'm just going to call it f of x. And I'm going to say, what is the area from, let's say, 2 to 8? Well, what I can do is I can do a rectangle approximation. And so if I take the shape of a rectangle, and if I start from the left-hand side, and so let's say I make a rectangle here, all right, that's of width 1, and then I make another rectangle from the left-hand side, and I hit the function on the left-hand side of that rectangle, that's also of width 1. And we continue that process on the left-hand side like this. Maybe I should have made it only from 2 to 6. That might have made it a little shorter work. All right. Now this is called a left side approximation of the area under the curve. Now, if I've found the area of each of these rectangles, I would find an approximate value for the area under the curve. But we can clearly see that there is some error. And in fact, this thing is going to be an under approximation because that's going to be missing. This is going to be missing. This area here will be missing. This area right there will be missing. This area right here will be missing. And this big area right there will all be missing. And I don't know why it's snapping like that on me. It shouldn't be. Especially if there we go. Maybe that'll do it. Okay, so all of these areas are missing in that case. So if I use this as my approximation, that would certainly be a under approximation. Now we could come in from the right hand side. So let's say let's get rid of all. Ooh, I didn't want to do that. Oh well. I just wanted to get rid of when that's while I'm at it, I might as well get rid of all of these rectangles here. Maybe I can do that. No, I'll do them one at a time real quick. Oh, you son of a gun. All right, let's draw that back in there, and we'll still go from 2 to 7. And we'll do something like that again. Now, if I wanted to do a right side approximation, well, basically what that means is I am going to use the function value from the right-hand side to draw my rectangle. All right, so at 7, I go up to the function, and then I draw my rectangle towards 6. I start at 6, I go up to the function, I draw my rectangle towards 5. I go up to start at 5, draw my rectangle towards 4, start my rectangle and then this last one, draw my rectangle to the function and go that way. And now this area is going to be an over approximation. Now it's going to depend on the curve to decide which, either the left-hand side or the right-hand side will be the over approximation. It just happened to be that way because of the way that I drew this function. Okay, so that gives us just a general idea of what I mean by left side and right side approximation of an area under a curve. So let's review some sigma notation here, one of the second ideas. And so when I say this thing here, this says the sum from 1 to n of all of the values a sub I. All right, so I is my index of summation. That's what's actually doing the counting. A sub I is the ith term of the sum, whatever that is. 1 in this particular case is the lower bound, and it's usually 1, but it could be anything. It could be 0, it could be 100. And n is the upper bound, whatever that is. And then we don't know, they could give you a value, they could let it go on forever. Some formulas, and you certainly want to know at least the sum of n constants, definitely the sum of the consecutive integers and the sum of the consecutive squares. This one might be a little much, but we're going to look at it later. And so certainly you want to have these in your long-term memory. All right, so let's move to here. First example, and I am going to... Okay, and we're back. There was just a quick pause. Anyway, so let's talk about this one right here. It says use left and right endpoints and a given number of rectangles to find two approximations of the area under the curve. Now I picked this one because we can actually calculate the area under this curve by hand. So just kind of to give you a general idea of what I'm talking about here. All right, x minus 9, or 9 minus x, is a linear equation that looks kind of like this. And you know what, let's see if we can't make our lines a little smaller here. So I've got a line here, I got a line here, and we'll call this right here 2, and we'll call this one right here 6. So that's where we're at. And so what this question is asking you to do is to use left and right endpoints to give the number of rectangles to find two approximations of the area under the curve. Well, the area under this curve is a regular value. We can actually calculate this. We know that that thing is a trapezoid. And the area of a trapezoid is A equals 1/2 height times B1 plus, oops, let's go back just a little bit, B1 plus B2. Now, in this particular case, since our trapezoid is kind of, the parallel lines are vertical in this case, our B1 is f of 2 and our B2 is f of 6 in this particular instance. And those two values, so when I plug 2 into this, I get 7 out. And then when I plug 6 into this, I get 3 out. And then the height would be this distance right here, which would be 4. So I can actually calculate this. So A half times 4 is 2, 7 and 3 is 10, 2 times 10 is 20 units squared. So that's my actual value, and I know that. And again, we're doing an easy one here because if there's a curve, we couldn't actually calculate it using this method. So we want to use left and right endpoint given the number of rectangles to find two approximations of the area and the curve. So we have a left approximation and a right approximation. Now, the problem with this one is that the distance between these two is 4, but they want 6 rectangles. That's not a real nice number. Since our distance is 4 and they want to divide it into 6 intervals, that ends up being 2/3 per, is going to be our constant width. And if I do that, I end up, so 2 in terms of thirds is 6/3. So we get 8/3, we get 10/3, we get 12. Is it 12? It's going to be 12/3. I think it's, yeah, 12/3, which would be 4. 4 in the middle. I should erase that, make that look nicer. We have 4, which would be 12/3. And then we would have 12/3, so 14/3. Then we'd have 16/3, and then 18/3 is 6. Okay. Now all of these have a constant width of, let's see here, it'll be 2/3. All right. So what I did is I used my calculator and I made a table. And so when I made that table, I picked my values of x. I put my values of x in right here. So here's my x's. They were 2, they were 8/3, they were 10/3, they were was 4, then 14/3, then 16/3, and then it was 6 there at the bottom. And so those were my x values. My y values, I then calculated those. I just plugged them into this equation. And so this one, it ended up being ninths, or no, I'm sorry, that was wrong. It comes as 7, and then it was 19/3, and then it was 17/3, and then it was 15/3, which ended up being 5. And then it was 13/3, it was 11/3, and then 9/3 was 3, which is what I had right here. So I know that those are right. All right, so if I want to find the area of a rectangle, and so let's talk about a left side approximation in this case. My first rectangle would be the height, which in this case was 7, times the width, which in this case was 2/3. So when I say my width, talking the change in x, that's my width for each of those. And so it's 2/3 for each of them. And so my area of the rectangles, A-R-E-A, that's an A, ends up being this 7 times the 2/3. Now I did it in ninths just so that I could keep them. So this is actually 21/3. 21/3 times the 2/3 is, it's 42/9 is the area of this rectangle. And then the next rectangle there, that rectangle there would be, let's see here, what did I have? So 38/9, and then I would have 34/9, and then it was 30/9, and then it was 26/9, 22/9, and then the last one was 18/9, which would have been 2. So if I do my left side approximations here, I notice that I have 1, 2, 3, 4, 5, 6 left side approximations. So that's actually these first 6 rectangles. That's going to be these. And so when I add all of these up, all right, these first 6 rectangles, they add up to be 192 over 9. All right, so this is my left side. Now, if I do the same thing on the right-hand side, all right, and again, let's pick red and change our line a little bit. This one is going to start here and go over. Then it'll start here and go over. Then it'll start here and go over. And this one will start here and go over. And then this one will start here and go over. And then this one will start here and go over. Now, if you look, this red triangle right here is the same as that red or the black triangle right there. So my right side approximations are these 6 rectangles. And so this is my right side rectangles. And their sum, when you add them all up, that comes out to be 168 over 9. So my right is 168 over 9. And both of those approximations are close. This one's 21 and a third, and then this one ends up being 18 and 2/3 when you reduce those two fractions. And since we already figured out that the actual area was 2/3, the left side approximation, as you would expect, because of the extra on each of those rectangles, would be an over approximation. And the right side, because these rectangles are a little bit beneath the line, would be an under approximation. Again, we should probably have units squared for both of those. Okay, so we're talking about finding the limit, and we're going to see that a lot of these limits use the same properties that we used in the last particular lesson. So we're trying to find the limit of s sub n. Oops, I don't really like that. Let's write it better. The limit of s sub n as n goes to infinity. Now, I don't want to multiply all this stuff out. It's kind of a pain in the butt. But I do know that eventually I'm going to multiply 81 times n times n times 2n. And so I know that this limit will be the same as the limit as n goes to infinity of, let's see here, it'll be 162 n to the third. Now there'll be other stuff, and I know that there'll be other stuff. But again, we're talking about the highest degree term is going to be n to the third. On the bottom, it'll just be n to the third times 6, which would be 6n to the third. Now again, I know there's more stuff here. But in the context of a limit, the only ones that matter are the coefficients of the highest degree terms. And so this limit is going to be 162 over 6. And I'm not sure if 162 goes into 6 evenly. So let me grab my calculator here. 162 divided by 6. Hey, it goes in evenly. It's just 27. So there's that limit right there. All right. So yes, I could multiply all this stuff out, but the rest of the stuff doesn't matter. It's just the coefficients of the highest degree. Now, if I ended up with 4 here and a 3 in the denominator, as far as my degree goes, that limit would not exist, or it would go to infinity. If it ended up being 162n squared over 6n to the third, well, then this would be 0 because the degree of the denominator was bigger than the degree of the numerator. All right, last one of the day. This is another limit involving a summation. And so we need to discuss it in terms of both the summation as well as these equations that we had talked about earlier in lesson. So let's talk about what we have here. This says the limit as n goes to infinity, and I've got n as my upper bound. Now, this is going to sound kind of odd, but in the context of this summation, which would be the 2i over n times 2 over n, the n in the context of the summation is fixed. In the context of the limit, it goes to infinity. In the context of the summation, the I changes, but the n is fixed to whatever that top number is. All right, so it's kind of like a composition of two functions, a summation and a limit. And because in the context of the summation, the upper bound is fixed, we can consider it to be a constant and move it out, just like we can move these 2's out. So I can rewrite this limit here as the limit, and again, you have to write your limit until you evaluate your limit, of 4 over n squared. Okay, so n times n gives me the 4, or n squared. 2 times 2 gives me the 4. I can't move the I out because in the context of the summation, the I is my index. It's my counter. It's what changes from all the values from 1 to n. Now, when I factor out these two 2's and get the 4, and I factor out these two n's and get the n squared, all that's left is just I. All right. Now, we know from this list of equations that if I take the sum from I equals 1 to n of just I can replace it with this equation here, this n times n plus 1 all over 2. So we're going to do that. We're going to say that this is equal to the limit as n goes to infinity of 4 over n squared, and then it's going to be n times n plus 1 all over 2, because I'm just replacing this expression with the equation that we had for finding this sum. And so again, I end up with something similar to what we had in the last problem. I know that it's going to be equal to the limit as n goes to infinity. Well, I'm going to have 4n squared on top, and yeah, there'll be some other stuff. All right, but it's that highest degree term that I'm worried about. And I have 2n squared on the bottom. There's nothing else, but it wouldn't matter if there was some other stuff there too. Since the degrees of the numerator and the denominator are the same, the limit as n goes to infinity is just going to be the ratio of the leading coefficients, which in this case is 4 over 2 or just 2. So that's that particular problem. All right. We have come to the end again. So the Star Wars Super Fabu fun fact of the day. In The Empire Strikes Back, Darth Vader employed some bounty hunters to try and find Han Solo and Princess Leia and Chewbacca and I think C-3PO. Yeah, C-3PO is in there. And he called these bounty hunters up on his Star Destroyer to try and find them. And I just thought I would reveal the names of all of these 6 bounty hunters. Most people know Boba Fett, but they all have names and they're all in canon. And so there's Darth Vader. This is Dengar, IG-88, Boba Fett. This guy is Bosk. He's wearing, for those of you Whovians, he's wearing an old Whovian, an old Doctor Who costume. Forlom and Zuckuss, and all of these guys have had stories written about them. They're all legends now, but there you go. That is it. That's all I got for today. I hope you have a good day. Goodbye.